Very, very roughly.
Yeah, just don't go to drill class.
Sure. We're not gonna spend a lot of time on this. Very, very roughly. What you want to know, it's not enough to know that an L function has a functional equation and Euler product and analytic continuation and Euler product and moderate growth and growth rates. I mean, there's some conditions that you need growth rates. It's not enough from these facts to conclude that then this is the L function of some automorphic representation. But if this has degree n, if L has degree n, a degree n Euler product, and for all, in some sense, we have to make this precise, degree at most n minus 2, it turns out, representations rho, L of pi, the Rankin-Selberg L function, the twisted L function by rho, so whatever this is, also has functional equation and Euler product. Then the original, then there does exist a pi, a representation, automorphic representation, such that, well, let me just call this, let me call this one a real, the real thing, such that the L function of pi is this hypothetical L function. So this is how, now, if you find in some Eisenstein series a constant term that for some weird reason looks like the symmetric fourth power of a GL2, and you can show that all of its twists, now symmetric fourth of GL2 is going to be a degree, no, 5 L function. GL2 itself is degree 2, symmetric square is degree 3, symmetric fourth is degree 4. Did I do that finger counting right? I think so. Anyway, so if you can show that all twists by GL2 have functional equations and analytic continuation and growth rates, then you can conclude by the converse theorem that in fact the symmetric fourth power is an automorphic representation. So that gives you the lift from GL2 to the symmetric fourth of that GL2 as a GL4, as a degree 4. So again, very roughly, it's not dissimilar to knowing, what does it mean to know an L function? An L function is Dirichlet series, right? You know a bunch of coefficients, these an over n to the s. And then what does it mean to say that there exists an automorphic representation? Well, okay, this is the distinction between automorphic forms and automorphic representations, but let's say there's an automorphic, so an automorphic representation is a vector space, pi v. So there exists a form in V, there exists a phi in V, such that, again, this is, everything has to be made much more correct, not just precise, but correct, such that this is something like a Q series. And so the construction from the coefficients of the Dirichlet series to the automorphic form, this is an automorphic form living in some automorphic representation, in some infinite dimensional irreducible representation, has some kind of an expansion, this a Whittaker expansion with Fourier coefficients matching the coefficients in the L series. So then once you create such a thing, the question is it actually automorphic? Is phi modular, for example, just to make it look like the modularity conjecture that we discussed, how you have an L function of an elliptic curve, and the question is, or the coefficients of an elliptic curve, the question is, when you put those coefficients into a Q series, is it invariant under a congruence group? Not invariant, but is it modular under a congruence group? So when you replace z, q is e to the 2 pi I z, when you replace z by like -1 over z, or whatever the generators are of your level, depending on the level of the congruence group, do you get modularity? Does that make some sense?
I don't know this stuff for this.
Makes sense to me.
Yeah. So the question of existence is I mean, okay, if you like, I can not this time, but I can next time give a version of a converse theorem. Would you like to see a converse theorem? Okay. Okay, so next time we'll do, maybe not next, at some future, in the future, I owe you a converse theorem. What does a converse theorem look like? So Bayes' converse theorem says that if you have something that looks like a GL2 modular form, and you know all of its twists, okay, so yeah, this is if n is greater than. So there's a converse theorem with twists by n-1 that's an easy converse theorem, and there's a much harder theorem that actually you only need twists by n-2. But once you're on GL2, you want GL1 twists. Well, GL1 twists are Dirichlet characters. So if you know that that you have an L function, and all of the Dirichlet characters are also, all of its twists by Dirichlet characters are also L functions, then the only way that can happen is if the thing itself is a modular form. I'll prove that for you on in some.
You know the twists are modular, you know they have function equation and Euler.
Yes, knowing that knowledge just on the level of L functions is enough to conclude something about, you know, automorphic forms, which then can produce automorphic representations.
There's a short answer. Why was modularity so hard?
How do you do it?
It's also doable.
I mean, it was doable because Wiles is a genius. You know, I don't think it's the kind of thing that, you know, there are some discoveries that like someone would have come along and discovered this. And there are others that had this, you know, had Wiles not sat down and just, today would we know Fermat if Wiles hadn't done it?
Yeah, we would. It's like 20 years. I think. It was like 20 years.
It's
Serves much of the
there's all, yeah, so the continuation of that project is, yeah. It's, I mean, these things you could speculate on ad nauseum, maybe not useful, but anyway. Okay, I'll show you I'll show you a converse theorem. I'll show you a converse theorem so that you get a feel for what it looks like. There's a nice proof in Goldfeld's other book of this GLN in level 1, but why, if you have a GLN, maybe he only does it for GL3, that if you have a GL3 L function, it's enough to know its twists by just Dirichlet characters to know that it is a GL3 automorphic representation. I'm trying to remember what, there's a general statement, I don't remember what's proved in that book, but there's a pretty down-to-earth proof of that. In Bump's book is a very down-to-earth proof of Bayes' converse theorem, which is this modular, you know, you have a modular form of some weight. Well, you want to know that you have an L function that's pretending to come from a modular form of some weight, and you know that its twists by Dirichlet characters also pretend. There's no way to pretend. You actually must have come from a modular form. So okay, I will, let me write it down so that I remember. Bayes converse theorem.
Is there any way of interpreting this as like saying certain functions are?
Yes, spectrally, yes, absolutely. So just knowing this L series is not enough to pin down the how shall I put this? Spectrally, just knowing the ANs is not enough, especially in higher rank, to be able to say something about the automorphy of the resulting series. Which is why if you have lots of twists, then that can capture this thing. But the Selberg class of all things that have Euler products and growth rates and functional equations and analytic continuation is conjectured to, it's conjectured that the only things that are in the Selberg class are the Langlands L functions of automorphic representations. And that's been proved for degree up to 2, maybe a little bit past 2. So, okay. Where were we? Okay, so back to the regularly scheduled. We were in the middle of proving the Iwasawa decomposition, if my notes are right. Yeah. So theorem Iwasawa decomposition for GL2QP, right? For every G in GL2QP, there exists a unique way of writing G as 1x01, P to the E1, P to the E2, K. X is in the adels. These E1 and E2 are integers. And K is in the maximal compact, which is GL to ZP. Thank you. I'm getting ahead of myself. That's next. X is in QP, and that's not enough. Okay, so I think we got as far as, let's just recall the proof. We didn't get very far. You start with your ABCD. If I want to multiply this by something like D negative C, but those will not be in ZP. I'm trying to multiply by K inverse on the right to get to something that's upper triangular. So I have to multiply by P to the L, so let P to the L be the maximum of the p-adic norm of C and D. Yep. So that if I multiply things by P to the L, at least one of these is a unit, is a p-adic unit. So I can fill this out. And then, so G times, let's call this, it's not the K that's going to go here. We'll call this K1 or something. So G times K1 is upper triangular. Right? Is that, remember we did this? And what should we call the diagonals? I don't know, T1, T2, and then something over here. T1 and T2, well, the determinant of G, to be in GL2, the determinant of G is non-zero. So T1 and T2 are non-zero. So T1 must be some P to the E1 times a unit. U1 is in ZP cross. And same thing with T2, P to the E2 times U2. Hey, so if I multiply this, so if I take G and I multiply it by K1, and then I multiply by, I'll multiply by U1 inverse, U2 inverse. That will leave me with just P to the E1 and P to the E2. So if I multiply that by P to the minus E1, P to the minus E2, that leaves me with something that's upper triangular. Equals, there's an equal sign missing. Equals something that's upper triangular with ones on the diagonal. Is that clear? Yeah. And the point is, this is also in K. So this is still in K. This is in K. So what we've done is we've written, therefore, there exists a representation of G as 1x01. Now I'll multiply on the right by P to the E1, P to the E2. These are uniquely determined. These are exactly determined because I said, let P to the L be the max of this. Then I multiply here. It's clear that T1 is determined because T1 will be this product plus this product. And hence T2 is also determined because the T1 times T2 is the determinant of G. So far I haven't made any choices. Times an element of K, let's call this, I don't know, K2 or something. K2 in KB. The question is this unique? Is this unique? And the answer is no. So let's see why not. The answer is no. If I have two different representations of G, if G is also equal to 1x1 prime, P to the E1, P to the E2. Now, E1 and E2, well, okay, let me put primes here, and in a second we'll prove that they actually must have been the same. It didn't. So what I'm saying times an element of K, I'm going to call this K prime. Let me not write K2. Let me just write K here. And this is K prime. Okay, so we've expressed G as a product like this. If there's some other representation, I want conditions on things so that X must equal X prime and E1 must equal E1 prime and E2 must equal to E2 prime, and hence K prime must equal to K. Okay, this is what I want, the uniqueness.
Just as nothing yet, so the non-trivial possible.
But they're both equal to G, and so they're equal to one another. So here's what we can do. I'll multiply by the inverse of this over here, and I'll multiply the inverse of that over there, and I'll multiply by the inverse of this over here. So I think what I'm going to get is K prime times K inverse. And the purpose for doing that is that this is in KP, this is in GL2 ZP.
So that gives you information.
That gives me information. On the other hand, I have P to the E1, P to the E2, 1x0, 1 negative x prime 0, 1, and P to the minus E1 prime, P to the minus E2 prime.
So you can conjugate that with mean.
I'm getting a conjugate of this thing, has to not have any denominators, has to be in ZP, no powers of P, no negative powers of P. Okay, let's multiply this out. Well, this is easy to multiply out. It's a group. So I get 1x minus x prime 0, 1. And now I'm going to multiply. It's not actually conjugation because there's an E1 prime here and an E1 here. So what will we get? So we're going to get this product. On the diagonal, it's easy to see what we're going to get because the diagonal has ones here. So I'm going to get a P to the E1 minus E1 prime and a P to the E2 minus E2 prime. The only question is, what do I get here? And I think what I'll get, there's a P to the minus E1 prime there that's going to multiply X minus X prime, and then a 0. And here, what I will multiply by is a P to the E2. When I compute this product, the 2-1 entry will come out to P to the E2 minus E1 prime times X minus X prime. Okay, so if you want to do that more slowly, please be my guest. Okay, so this thing has to be in GL2ZP. That means P to the E1, that means E1 minus E2 has to be positive. And for the same reason, E2 minus E1, E2 prime has to be positive because they have to be elements of ZP to begin with. Moreover, their product has to be invertible. The determinant has to be invertible. But the product means that E1 minus E1 prime plus E2 minus E2 prime actually has to be 0. Right? Determinant of G has to be in ZP, has to have p-adic value 1. But the only way to do that is p to the 0. So I have two positive numbers adding to 0, the two numbers must be 0. So we proved that E1 equals E1 prime and E2 equals E2 prime. So I gave you an algorithm for how to compute E1 and E1 prime, E1 and E2, but there is no other algorithm. There is no other way to decompose G in this way with a different E1 prime and E2 prime. Okay, great. So at least that part of it is unique. But so now we have that E1. So now we have that these two things are equal. So now I have 1, 0, 1, and then P to the E2 minus E1 prime, but E1 prime is E1.
The problem is not coming.
The problem is not coming from the E's, it's from the X's. This thing has to be an element of GL2 ZP, which of course is true if and only if P to the E2 minus E1 times X minus X1 is in ZP. And what I want is that I want this fact to force that X is equal to X prime.
Maybe we did that.
then this, if this is, then this would have to be 0. In which case, so in which case, this is the identity, in which case, K prime has to be equal to K. So how can the fact that this product is in ZP force that X is equal to X prime? All I know, you see, if I write X as some A minus N, P to the minus N, and so on, A minus 1, P inverse, plus A0, plus A1, P, and yada, yada. And I multiply, and I have the same thing with X prime, and I take their difference, and I multiply that by P to the E2 minus E1. I don't know if that's a forward product or a backwards product. I have no control over. E1 might be bigger than E2, less than, they could be negative, right? They're just integers. Whatever this is, I want the fact that the difference multiplied by this has no forward stuff, has no denominators. And that should imply that actually they're identical, which means there can't be any, which means if it's in ZP, that element of ZP should be 0. Okay, so think about it for just a second. What we need is to restrict, we need to restrict X to something of the form. I don't know where it starts, but I can only go up to a coefficient so that when I multiply by P to the E1 minus E2, I guess plus 1. So this is the A E1 minus E2 plus 1 coefficient. So that when I multiply this, so if X is like this, if X has nothing plus zeros everywhere else, if X is restricted to have no, i.e. For all N greater than E1 minus E2 plus 1, AN of X, the coefficients of X are 0. So it has no tail. Assuming you restrict to that condition, X prime also has no tail. The difference between X and X prime also has no tail. And when you multiply by P to the E2 minus E1, you get something that at least has a P in it.
Yeah.
For that to be in ZP means all of the digits have to exactly agree.
In other words, 0
So the difference is exactly 0.
for X and X.
Yes. You see that? You see how we came up with that condition? So if we restrict X to something like this, then X prime is some other A minus N prime, could start somewhere else. And this is a coefficient prime going up to, at worst, E1 minus E2 plus 1, P to the E1 minus E2 plus 1. So it has to stop at the same power of P.
Can we like ask for that?
Sure. So what we'll do, this will be unique. This will be unique, and we insist that X, if written in some series, has A of N equals 0 for all N greater than, once E1 and E2 are determined. Was it E1 minus E2 or E2 minus E1? I always forget. E1 minus E2 plus 1. Which I can say strictly greater than E1 minus E2. In other words,
But for any G, does this choice exist? I guess what I want.
yes, very good. Good question. Good question.
Like, sure, if you had it, then we're done.
Yep. Let me come back to that in just a second, Nick.
How can we? Well, does X prime go up to E2 minus E1 then?
X prime goes up to the same thing as X, so it has to stop at the same place. E1 minus E2 plus 1.
So like
Is-
if we done this on the other side, we would have ended up with E1 minus E2 X prime minus X. Or determining that matrix. If we move things to the right side, and then our K on the left side instead.
No. Either way, we would have gotten, it's more about where their placement is. We would have gotten primes over here, a prime there, no primes here.
Okay.
Yeah. It has to do with,
There's not finding one.
yes, yes. And the E1s and E2s we already showed have to be neat. But to Andre's question, how do we know that we can find such an X? Well, that's exactly the amount of X that you can pull through the A part and still have it go into the K part. That's the non-uniqueness here, is that if this has a long tail, then that tail conjugated through this element will be an element of K on the other side. I'll make that explain. Yeah, let me make that explicit. So whatever this X is, yeah, let me make that explicit. And so let me just finish writing what I was saying here. If we restrict X to have this condition, in other words, all the coefficients higher up than this number, that's a minus sign, vanish. Then if X prime also has this, then X, yeah, X minus X prime times P to the E2 minus E1, the p-adic absolute value of this is at least P. Sorry, +1 takes me into ZP. You're absolutely right. I want -1 to make sure I have at least one negative power. I want at least one negative power. Thank you. And up above as well. And I'm sure. So wait, do I want this? I'll just play it safe and put exactly the condition instead of thinking about getting rid of the strict. Yeah, that's what I want. Right. I want to have at least, when I multiply by E2 minus E1, I have at least a P in the expansion. Well, it's at least P unless they're all zeros. Right?
Yeah.
Then this, unless all coefficients agree, unless all coefficients agree, i.e. X equals X prime.
And then X prime equals this, that's just forced from this having to be in GL over ZP.
Yes. Yes.
Otherwise, like X prime isn't even.
Yeah. So, but how can we find such a guy? So here's what I'm saying. If you write, so how should I put this? Write any X as some coefficient P to the minus N up to this point, A e to the E1 minus E2 minus 1, P to the E1 minus E2 minus 1, plus, now I'll write this as P1 minus E2, P to the E1 minus E2 times anything, U. U is in ZP. Okay, so I'm saying pull out the first coefficients, whatever they are. I mean, it might be empty, it might be vacuous, it might be, there could be some negative bits, and then, but I don't have anything past that. I don't want to have anything past that point. Let me write this as X naught. So the point is U, no, what I'm saying is plus the rest. So the rest,
We want to be in.
what I'm saying is any X can be written as something of the form that we want, plus the rest. So we've written X, we have written,
Yeah.
we have written G as 1x01 times P to the E1, P to the E2, K. But X at the moment, we haven't made it have the shape that we want. So my claim is that we can write, so because of this, we can write X as X0, which is of the good form, times 1 P to the E1 minus E2U, 0, 1, and then P to the E1, P to the E2, K. I've done nothing. This is just the fact that this is an additive group. the upper unipotent. Right? When this multiplies, I just get x0 plus this thing. Well, x0 plus this thing is x. And the point is this can get moved over to the k. So let me show you how you do that. It's a very simple trick. I'll pull the, I want to put the p to the e1, p to the e2 next to the x0. But I can't just do that. I have to pretend it wasn't there to begin with, because it wasn't there to begin with. In other words, I'm inserting the identity here. And then I have 1 p to the e1 minus e2 u, 1, 0, and then p to the e1, p to the e2, k. In other words, I'm conjugating this thing by this diagonal element, p to the e1, p to the e2. But what is that conjugation? When we work out what that conjugation is, so on the diagonal, I'm still going to have 1s and 0s. And by the same process as before, this is going to take off a p to the e1. This is going to take off a p to the minus e2. And you'll be left with u. I'll let you do that calculation more slowly if you like. So then you get times k times p to the e1, p to the e2, 1 x0, 0, 1, g. And this is in k. So whatever the tail was, you can conjugate the tail. That's the freedom that you had. You had exactly that much freedom to move things into the compact part. So move it out, and then you have something that has no tail. And now it's unique. I like to highlight where there are ideas and where there are where things are just like what you should get when you follow your nose. This I don't think is an idea. This is you follow your nose. Oh wait, I'm not getting uniqueness. Why aren't I getting uniqueness? I have too much freedom. That's right. Yeah,
So it could have been like a really nasty computation or like,
that's right. That's right.
somehow it like the questions were very natural, right? You sort of check this out, you see like either the conditions, you didn't have to get
It could have come out badly and it didn't. Which is probably why we study the subject. It's a beautiful subject. The things that we choose to focus on are the things where you ask a natural question, the answer is beautiful. If the answer is some god-awful clunky thing, you're like, do something else.
That's sort of what I meant when I said this is amazing.
It's amazing. Yes, it comes out nicely.
Because it isn't, it's like the same, we're mimicking the strategy with the classical case, but ultimately it's a different object, right?
That's
It
right.
still works.
That's right.
Many
That's
times when you do these sort of things just don't work, right?
Yeah, I guess you get jaded after a while of seeing that, when you do things piatically, it looks just like the real, well, once you have the right viewpoint. And the right viewpoint, let me emphasize where I do think there's an idea that GL2ZP is the right replacement of SO2 as the
Without
compact.
that, this whole thing doesn't go through.
Yeah. If you try to use something like an orthogonal group here, I mean, you just. So that is where I think there is an idea. That's where Iwasawa deserves credit for understanding the right way to do it. And then you follow your nose.
Yeah, exactly. Like, once you have that, everything goes through.
Yes, but the history goes. Yeah. I think Iwasawa was looking at this stuff before people understood, maximum Torah productive groups. I don't know if that's right. I don't know if that's right. Bourbaki was certainly thinking about reductive groups before that. Yeah, anyway. Well, were they thinking about it piatically? They were maybe thinking about reductive real groups. I think, Tate is like where we start attaching adelic things to reductive groups and semi-simple groups and stuff. Anyway. All right. Good. Let's go. Definition. Now that we understand the local places, we know how to decompose GL2R, we know how to decompose GL2QP. Of course, we're going to think about GL2 of the adels. What is GL2 of the adels? So this is really interesting because I wonder if it's in lean yet, because now we're really going to hit some serious issues. On one hand, you should define GL2 of the adels as GL2R times the restricted product of GL2 QPs. In other words, this is an infinite sequence, G infinity, G2, G3 of matrices where GP is in GL2 QP for all P and GP is in GL2 ZP for almost all P.
And then QP condition, again, was just making sure.
Well, that's what-
It's not literally here.
that's right. That's right. Right? Sorry?
A second guess.
That's be your second guess. And what would be your first guess?
Two I should make it to the adult.
Exactly. Exactly. And this is why I say this is where it gets hard when you try to formalize. Because sometimes you want to think about it this way, and sometimes you want to think about it this way. They are. So if I want to take A, B, C, D adels, and I want to know that the determinant is invertible, right? AD minus BC is in the edels. Why? So the fact that these two things are equal is actually a theorem. This is not obvious. Why? First of all, why isn't it obvious that these two things are the same? Right? These have their own, these have like each element of the adels is an infinite sequence, a real, a two-adic, a three-adic, and so on, where all but finitely many are in ZP. There's a different place where this one stops being in QP and starts being in ZP versus this one versus this one versus this one. And this determinant is also some invertible numbers, and then at some point it's in ZP crossed. Why is that the same thing as matrices in GL2 QP, but at some point all of the entries are in ZP and their determinants are units?
I guess I can I get. Bottom one's not this thing is eventually.
You mean the top one?
I know
In this formulation?
in the body, so if we take ABC and split it with product and matrices, right now that it is a thing that is eventually. But there'll be matrices and
Because all the entries,
all the entries are eventually easy.
because there's only finitely many objects.
Right.
So if you say eventually, you know, finitely many things can go wrong, times finitely many objects, that's still a finite number. So after the maximum of where this one stabilizes, where that one stabilizes, that one, and that one stabilizes, you are now in the elements are in ZP, all four, and the determinant is a unit. But that's exactly what it means to be in GL2 ZP. So that's the theorem. The theorem that these two things are the same. And a unit almost everywhere, yeah. Oh, and invertible everywhere in QP and unit in ZP at all but finitely many places. Right, which is what an edel is.
Right, yeah.
So they just work out. The definitions just work out so that this is, you know, so let me say this is a theorem. Right, this is a theorem, and the proof is that, you know, finitely many, finite cross finite is finite. But it's
It would be nasty and mean
for many reasons, this would be rather nasty and lean, especially when you want to go back and forth between the two different interpretations of what GL2A means.
A bunch of like subscripts.
Right,
and stuff like that,
right. Two G sequence, two entries. Well, there you go. So I don't know if this, I know that the adels and edels are in lean. I don't know if reductive groups on adels and edels. That's it.
The next thing after you get the prime number theorem really generally, then.
Right. Anyway. Okay. So is this clear? So which one of these you want to take to be your definition? Now we've proved that the definitions are equivalent. But that really is a theorem. It's not.
Yes, it doesn't like fail the same way that like the two topologies on like,
That's right.
the edels
That's right.
fail.
That's right. We don't have that.
Because those are non-uniformity.
Right.
And here like, it's good enough to get uniformity.
Yeah. Okay. And let's get the Iwasawa decomposition. Iwasawa, so adelic now, adelic Iwasawa decomposition for all G in GL2 of the adels. Hopefully you see this nothing to do with two. These are general theorems that I'm proving for GL2 for simplicity. There exists a unique decomposition of G as. So I will immediately start using this version to describe these matrices, even though the original definition was over there. You see how this starts going. How do I want to say this? Okay, so let's say 1x01, y001.
One is just like one in all the entities.
That's right. That's right. There's a unit in the adels, in the edels, times k. Where? Okay, so x is in the edels. X infinity, x2 is, I'm sorry, in the adels. Y, again, is a infinite product. That's in the edels. R is an infinite product in the edels. And K is in the adelic compact, which is the product over all the compacts. The GL2R compact is O2, and then a product over all primes of GL2 ZPs. Now they're all compact, so I don't need a restricted product. It's already restricted to the compacts.
In the O2 part, you're just taking the Iwasawa from
That's right.
the real.
That's right. That's right. And we're not done because we weren't done p-adically. Right. Let's say RP. The pth place of R is P to the E2 of P. I mean, there's an E2, there's different E2 for each P. And the E2 of P is equal to 0 for almost all P. YP is equal to P to the E1 minus E2, correct? E1 of P minus E2 of P, and E1 of P is 0 for almost all P.
His RP is in places of R.
Right, R just like, yeah.
Yeah.
And XP, oh, and R infinity is positive. R infinity is positive. Y infinity is positive. So R infinity and Y infinity are positive real numbers. That if there's a minus sign, it goes in the compact. I mean, it's in -1 is in O2. And what can I say about the XPs? That once I know what the E1 and E2s are, I can say that XP and XP, so X infinity is just in R. There's nothing I can do about X infinity. And XP is a sum of some coefficients AL, well, P times P to the L, where L ranges from minus NP up to E1 of P minus E2 of P minus 1, right? It was -1 that we wanted as the last power. Okay, that's the theorem.
So
That's the theorem. And the proof is 0 lines. We've already proved it. Right? There's once you just do the decomposition in each place, and you do it place by place. Proof is local to global. We know that there is such a decomposition at every local place. When you multiply things in their place, that all commutes, you know, unless you're working in the same place, there's no difference whether you multiply before or after.
just that, like, you know, concrete in practice.
No,
There's so many conditions really floating around.
no, because the way you're going to think about it is this. They all help you. and this is unique. It's just basically, when you just want to talk about the edels themselves, they don't talk, except for the fact that you're restricted in how many places you're outside of GL2QP, GL2ZP. So remember, for all but finitely many places, you're just in, the answer is K.
So that's,
Like this is in ZP for almost all places. This is P to the 0 for almost all places. These are P to the 0 for almost all places.
that's, at once you hit them for almost every, then this is trivial.
Yes.
This is handling the non-trivial.
Right. There's only finitely many places where this applies, and then everywhere else you're just in K. Does that make sense? Okay, so that's not what's interesting. What's interesting, the Iwasawa decomposition is not interesting anymore, now that we've worked out what it should be for locally, globally, it's all the same. Let me remind you that GL1, not GL2, but GL1 of the adels contains GL1 of Q, the diagonal embedding, let's say I diagonal, the diagonal embedding of GL1 of Q is contained in here as a discrete subgroup, and we worked out a fundamental domain for the quotient. Right, this was edels modulo rationals. What was the fundamental domain for the quotient? This is edels modulo rationals. Zero to infinity. It's the multiple. This is R cross mod Z cross. Z cross is just plus or minus 1. R cross is everything but 0. So you can make things positive, and then ZP crosses. Okay.
What did we set this up for the unfolding stuff?
Yes. That was the application was to various cell function
Right.
calculations.
Analytic.
Dirichlet functions, zeta functions. So, yeah. Okay, so I'm just reminding you what this looked like. So now what we want a fundamental domain for GL2 of the adels with the discrete subgroup GL2Q inside. What will it look like?
GL2Q, like discrete.
And GL2Q.
As.
Yep, Q is discrete in A.
Yes.
So GL2Q is going to be discrete in GL2A, and we'll write down an open set, which is a fundamental domain for its action, which is one way to show discreteness. Say it one more time. Yes. Well, it's an alternate, right? So now we're going to have another decomposition of GL2A, not in terms of just Iwasawa itself, in terms of unipotent, abelian, and compact, but you know what happens if we can put a rational matrix or the embedding of a rational matrix in front. Okay, so let's work this out. Should I state a theorem and then the conclusion of the theorem is unknown, or let's work it out and then we'll state the theorem. Okay, so i.e. given a matrix in GL2A, how simple can we make it? How simple can we make it by multiplying by left multiplication by GL2Q? Okay. Well, this may be not a great thing to jump right into, but whatever. All right, so what's the first thing we might want to do? What's that? Yeah, let's get rid of the determinant. One of the first things that might be, so let's look at determinant of G. Determinant of G is an edel. Wait a second. We know a decomposition for edels modulo multiplicative rationals. That's exactly this. Okay, so the determinant is an edel. That means there exists a q in the rationals and an x in 0, infinity, such that the determinant of G is equal to q times x. I don't have to worry about the order because GL1 is abelian, but I'll write it in the proper order. Q is on the left, and then what's left is an element here. Let me be a little more precise about this.
You just factor in the determinant.
I am just factoring the determinant as a rational number. Yes,
You haven't done anything. You haven't acted by anything.
I haven't acted by anything yet. Let me be a little bit more precise because this is an edel or an edel. This isn't. So what I really mean is that I can write the determinant of G as the diagonal embedding of Q, right? I can embed Q into every place times the infinite embedding of X. So the infinite embedding of X is, I only put X in the infinite place. I don't know what to do with a real number at the two-adic place. There's no way to, I just put ones everywhere else. Okay, so I diagonal of something means I put Q everywhere, including infinity. I infinity of something means I only put it at the infinite place, and then I put ones everywhere else. I don't do anything at the other places. Okay, so this product will get me my favorite element of this. Okay, that's this this decomposition. Now, what? So i.e. If I take G, I want to left multiply by an element of GL2Q. So I'll multiply by Q inverse and then 1. And I'll right multiply by X inverse and 1. Yes. Yes. So what I really want is that this, I can make the X term exactly 1, and then I have something in ZPs. So this equality, yeah, times something in ZPs, times U, which is in the finite adels. So U is of the form 1, and then something, an element of ZP for all P. So when I multiply by a rational number, I can get, I can take an edel, multiply on the left by a rational number. Of course, it doesn't matter which side I multiply by. And I'll get something that's in all ZPs and some real number between 0 and 1. Well, if I multiply by that real number between 0 and 1 to make this thing 1 on the nose, so that's multiplying by X inverse, and multiplying by Q inverse will get me something that is 1 in the real place and then in ZP for all the other places. So that's actually what if I want to make this an equal sign, then I have to multiply by one more thing times U. Okay, the Q will handle any parts of the edel that's not in ZP. The X will make the infinity entry 1 on the nose. And then I have infinitely many elements of ZP that I can't do anything with. In fact, ZP cross, because this is an edel. Okay, so if I take this Q inverse times G times X inverse, what is the, so let's call this G1, i.e. let G1 be this, then G1, what's the determinant of G1? The determinant of G well, the adelic, so these all have norm 1. What's that? Yeah, so I claim I can get this into SL2 of the Adels.
Well, then you, all right, I guess determine the
So we've killed the Q and the X. All that's left is something with absolute values 1 everywhere.
This is like after having. Where you factor G, the G,
Yes,
and then you're multiplying
I'm multiplying off. Yes.
specifically so that.
Well,
part gets built off.
The reason I'm multiplying by this on the right and not on the left is this is an element, this is in GL2Q, but this isn't. And I'm trying to understand what the decomposition of GL2A now on the left by GL2Q, and now it matters whether I'm multiplying on the left or right. So this other element, which is just, I mean, I should put an I infinity here also, if you like, because I'm only specifying an infinite iota infinity. This is only changing the infinite place and nothing else. And so this is an element. Well, I want to get a simple. I want to get a simple decomposition of G1. Okay, let's keep going a little bit. You'll see what's going to happen.
G1 and G2 are related in practice.
So you have G, the determinant of G. I can pick off a real part and a rational part. So if I multiply by the inverse of the rational part and the inverse of the real part, I'll get something with determinant 1, with unit determinant.
Oh, and you're saying that these. Okay.
I'm just defining G1.
Matrix is on, well, it's what we're acting by, so we're allowed to do this.
Yes.
Okay, that's.
Yeah. So now we need the strong approximation theorem. Strong approximation theorem.
I mean, it's easier, maybe it's easier to look first at SL2 for our factorization and then go to the so because like.
Yes, exactly. We're going to do an SL2 factorization, bootstrap that up to a GL2, and this is how you do that bootstrap. If you like, I can put the U also. I'll put a U inverse here since they're all invertible, and now it's literally the determinant has every entry equal to 1, if you prefer.
Like, and why do those things on the right not matter?
Well, they're going to matter. We're going to get a decomposition for G1.
Oh,
And then we'll be able to put that back into what can we say about G, the original G. We're going to build back up to the original G, but it'll be easier to work with G1 first. Okay, so let me tell you the strong approximation theorem. It's that if I take SL2Q embedded diagonally and I multiply by SL2R embedded at infinity, this product is dense in SL2 of the Adels. Okay, let's see why that's true.
the topology for SL2A is
The restricted topology of the Adels.
of the Adels.
So let's see why that's true. Okay, so what's an element? So this is the theorem. Strong approximation theorem. Proof. Why is this true? Well, what does it mean to be dense? Give me some open set, given some open set. So let's say U is the open set. What does an open set look like? It's a product over some finite number of UPs times every place that's not in S, I want SL2 ZP, where UP is a subset of SL2 QP is open. Okay, so the density is given some open set like this. So the claim we need to show that for any open set like this, there exists gamma in SL2Q and I'm running out of letters, matrix M in SL2R, such that gamma times M, by which I mean the diagonal embedding of gamma times the infinite embedding of M, is in U. Right? What does density mean? Any open set contains a point. Okay, an open set in the Adels is something that's just in the compact for all but finitely many places. In those finite number of places, I have some open in SL2QP.
It is sort of the principle is you can choose your open set to be really small.
Yep.
Then this is a good approximation.
Yep. That's what density is, right? Any open set, any non-empty open set contains a point in the thing you're claiming is dense. Okay, so let's try to first get something. What does it mean to be in UP? Each UP contains a set of the form, some gamma P. Gamma P is in SL2QP. Times or plus, depending on how you want to think about it. Yes, I can say plus actually. Plus P to some large power, like maybe LP, times just 2 by 2 matrices, M2 of ZP. Let me explain what I mean by this. What's an open set in UP? What's an open set in SL2QP? It's I have some, so if ABCD is in SL2QP, well, these are all elements of QP. And what's an open set? I might fix a bunch of digits, and then the rest of the digits are free. But the back digits don't change anything about the determinant. The determinant only cares about the leading digit of AD minus BC. This is not working R at all. That's right. That's right. I'm very much so. Right. You can perturb and stay in SL2. Yep, by the non-Archimedean norm. So what I'm saying is, what does it mean to be an open set? It's some fixed coefficients, it's some fixed numbers, and then the tail change by whatever digits you want when you go far enough down. Does that make sense? So the embedding, so what do we need if we want to find a matrix gamma that embedded into the p-adic place is in UP? So to find such gamma, need to solve a system, of equations that gamma is congruent to this gamma p mod p to the l, p to the lp. And we have a system like this as p runs over the finite set S. Does that make sense? What does it mean that you're in UP? UP contains, what does it mean to be an open set in SL2 QP? Okay, what are open sets? Well, it's some points where you've specified the first bunch of digits. That'll make sure that you're in SL2. And then the last digits are free. It's these cylinder sets again. And S is finite. S is finite. Well, that's the question. Can we do it? Yeah, if we can do it at one place, then we can do it yeah, these are matrices. So let me illustrate why this is subtle. So let's do an explicit example. I think I'm losing you guys. Explicit example. Okay, here's a matrix. 2003. This is a matrix in SL2 Z mod 5. Because the determinant is 6 and 6 is 1 mod 5. So this is in SL2 Z mod 5. Does there exist a matrix ABCD in SL2Z such that this gamma is congruent to 2003 mod 5? Okay, you know the answer, but. Right, this seems like, wait a second, I need to get something that's. Like this is in Z mod 5 only because 6 is 1. That doesn't mean I'm going to be able to lift this to the integers. How? 2, 5, 1, 3 will get us a 6 and a minus 5, but this 1 is not 0 mod 5. I want you to appreciate that this is not entirely trivial until you look at it from the right point of view, and then it is trivial. Yeah, we can just work it out directly. I want to see if you. Okay, so let's work it. Should we work it out? Yes. That's the right way to think about this. A must be 2 plus 5 times some A1. B must be 0 plus 5 times some B1. C must be 5 C1, and D must be 3 plus 5 D1. And then when you work out what the determinant is, AD minus BC, which needs to be 1, comes out to A times D is 6 plus 15 A1 plus 10 D1 plus 25 A1 D1. Minus BC is minus 25 B1 C1. Let's put that minus sign over there. So how do I make this do 1? 6 is 5 plus 1. So I can cancel the 1 on both sides. Almost. If I divide through by 5, let me just divide through by 5. So I get a negative 1. If I move this 5 to the other side, is 3A1 plus 2D1 plus 5 times this thing. If I can find an A1 and a D1, I can make this thing 0, for example, by choosing B and C to be the same as A and D. And how do I get this equation? Negative 1 and 1, I think, works. Okay, so A1 is negative 1, D1 is 1. I get negative 3 plus 2, and then I'll make B and C the same. So A1 is negative 1. That means I get here negative 3. Well, I just want, it's this 5. I move to the other side, and I divide everything by 5.
Okay.
I wrote 6 as 1 plus 5, so that 1 cancels off. So this is B1, I'll make the same as negative 1. So this is negative 5. C, I'll make the same as positive 1. So this is 5. And D is 3 plus 5 is 8. So let's see, does that work? Negative 3, negative 5, 5, and 8. This is 3, this is 2, this is 0 and 0, and negative 24 plus 25 is 1. Okay, so you can do it. Yeah. Okay, so you can do this. We can lift elements of SL2 Z mod 5. It's rather trivial, okay, and you can do this in prime powers, and then you can put them all together with the Chinese remainder theorem. Okay, so it's not entirely trivial, but yes, it can be done. So does there exist? The answer is yes. And then the Chinese remainder theorem solves this system simultaneously.
It seems like here you have a lot of flexibility when
Sure.
this particular example, and in general, when you read this, it'll probably be.
We're coming to that. We want a fundamental domain, so we want to have no flexibility. I mean, up to sets of measure 0.
It's like, what is this like? Something like unique of the translations or like some.
You'll see. Yeah, there is going to be some non-uniqueness. Okay, so let's remember what we. Oh, by the way. Okay, so let me do another example. Here's a matrix in GL2 5. GL2 just means I need it to be invertible. So how about 3, 4. 3 times 4 is 12. 12 is invertible, mod 5. Does there exist a matrix in GL2Z such that gamma is congruent to 3, 0, 0, 4 mod 5? So the answer is no. No. Okay, for exactly that reason. This determinant of gamma can only be plus or minus 1, which means I can get 1s and 4s, but I can't get a determinant of 2. This determinant is 2. 2 is not 1 or 4. Okay, so this is the difference between reductive groups. GL2 is reductive, SL2 is semi-simple. Yeah, let me not give you the explicit definition. If you take a semi-simple group is a product of simple groups. Reductive is if you take the quotient of it by its center, you get semi-simple. I don't know if that helps you. Think of GLN and SL. Okay, so the point is we could not have done this exercise in GL. We really needed to go to SL to do this exercise. Now we're not done. We're practically done, right? What have we done? At all the finitely many places where we need to find something. So the point is that gamma embedded diagonally will be in all of these places. And now I use my matrix in SL2R to make the SL2R place anything I want. Right? I'm not doing anything at the infinite place. I'm only embedding at the infinite place. I can make the infinite place on the nose equal to some element of U. Give me your favorite element of U, which is some finite number of these gamma p's, and then some matrix at infinity. I'll make that matrix at infinity on the nose equal to what you want. And then at all the other places, well, first I have to diagonally, so that I know what infinite place I have to put here to get me something that's an infinite place here. And then I just make M to be the inverse of one by the other. Do I need to spell that out, or is that clear? At infinity, you have full flexibility. This to be diagonally embedded, you have to choose those rational numbers before you can say what the diagonal embedding is, and that's exactly what this is doing. What this is doing. And these really are rational numbers because you have to multiply, to be able to solve this in Z mod P, you have to multiply by P to some power to make everything rational. Solve it there and then multiply by P to that power back. Is this clear, or should I write out the details? Okay. Okay, so that's the strong approximation theorem, that this product is dense in SL2A. Any open set, we can find a matrix in SL2Q and a matrix in SL2R that'll be inside your open set. Okay, we don't have an open set, we have a matrix, G1. So let's get an open set. So recall, G1 is this matrix Q inverse 0, 0, 1 times our original G times X 0, 0, 1. And if you like, let me put this unit back in here. So this has determinant exactly 1. The determinant is 1 everywhere. Okay, with the determinant of G1 is an edel, and that edel is 1, 1, 1, 1, 1, 1. So far, so good. I get myself, let U infinity be a open set in SL2R about the origin, about the identity. Then look at the open set G1 times U infinity times a product over all places of SL2ZP. Yes.
The quotient on the left by GL2, why do you have these on both sides? Why are we allowed to have things, G1, why are we allowed to have things on both sides?
Well, I'm not allowing, so I do want to only quotient G by things on the left in GL2Q. All I'm doing is multiplying by some matrices on the right, and I'll have to deal with those matrices in a minute.
I'll see this SL2 in leverage.
I will be, yes,
Because if not, then this is just not gonna work.
right. Okay, so I take this G1, which is in SL2. So the point is G1 is in SL2 of the Adels. And now I give myself a little open set in SL2 of the Adels. And in here, I can find this contains some diagonal embedding of an element of SL2Q times the infinite embedding of some matrix in SL2R. That's what we just proved. That's a strong approximation theorem. In other words, i.e., G1, what does it mean to be an element of? There's some matrix here. I can't call it U, I call this U. Epsilon. G1 times some epsilon infinity, epsilon 2, epsilon 3, yada, yada. That's it, that this is in there, is exactly equal to some, should I keep writing the diagonal embeddings of an SL2Q times an infinite embedding of a SL2R matrix. And now we're almost done.
Yeah, which is entry wise.
Yeah,
Diagonal
coordinate-wise multiplication. Okay, and remember what G1 was. G1, so now I can say G1, which was Q inverse 0, 0, 1. Here's the G that we're actually interested in. Then there was an X inverse 0, 0, 1 and U inverse 0, 0, 1. U has a 1 at the infinite place and is all units everywhere otherwise, is equal to gamma. I mean, I didn't write the diagonal embedding here or the infinite embedding here. Hopefully it's clear. Here I'm being a little bit more careful. And now I want to write G equals. So G equals, I have the diagonal embedding of this gamma. I have the diagonal embedding of this Q inverse 0, 0, 1. Not inverse now.
Yes, you're putting it.
I'm moving that to that side. I have my infinite embedding of M, and now I need to multiply on the right by U 0, 0, 1. Then I need to multiply by on the right by the infinite embedding of X inverse 0, 0, 1. Of course, it doesn't matter what order I multiply these because they commute past each other. This has a 1 at the infinite place, whatever elsewhere. This has an X, not X inverse, at the infinite place, 1's everywhere else. So these two commute also. And this is a matrix in GL2Q. Or the diagonal embedding. I'm going to stop writing the diagonal embeddings. It's clear that that's in GL2Q. Okay. So I can make this. What is this in? Again, these two commute. So I can put this over here. And here I get something in GL2R. This is in GL2R cross a product over P of GL2. Oh, and where's my epsilon? This was G. Sorry. This was G1 times epsilon times the epsilon matrix. So I need to multiply by the inverse of the epsilon matrix. Epsilon inverse over here. But let's think about what epsilon inverse is. It's epsilon infinity inverse, epsilon 2 inverse, and so on. This is still in, no, this is still in GL SL2 of the Adels. This is some open set in SL2 of the Adels. Okay, and then the infinite place I can take out separately and move it over here to the real place. And then these are still all units. So this is still in GL2 ZP. So let's summarize. We're out of time. Let me summarize. Summary. These epsilons are matrices. Yes, the epsilons are matrices in this product. Okay, so in summary, for all G in the Adels, GL2 of the Adels, there exists a gamma in GL2 Q such that G is equal to gamma gamma, of course, the diagonal embedding of gamma, times let me say it like this. If I invert this times G, I'll get into GL2R cross GL2QPs, product of GL2QPs. GL2ZPs. Okay, so GL2A mod GL2Q, I can get it into this form. The question is it unique? And the answer is no, and I'll have to explain what's the non-uniqueness. Is it unique? I keep stopping at the is it unique part.
What's gamma on the product of all those things?
Gamma is just the product of these two. Gamma is an element of GL2Q.
So that you can handle it.
Yeah, I'm saying if I multiply by the left on the inverse of this, I can, by acting on the left by GL2Q, I can get G into this thing. I can make it GL2R. I haven't done anything, but then here, I don't have a restricted product of GL2QPs. I have GL2ZPs everywhere. That's what's changed.
You use density.
That's right. Okay, is it unique? And the answer is no, and to be continued.